Alright. Now we can actually dive into some more applied questions. Here we're dealing with circuits now. The statement reads, suppose that the circuit in the diagram has been connected for a long time, then suddenly at time t equals 0, switch S is thrown from A to B, bypassing the battery. A. What is the current at any subsequent time t? B. What is the total energy delivered to the resistor? C. Show that this is equal to the energy originally stored in the inductor. And we'll see that all these things need to work together. But let's go ahead and look at our diagram. Alright, so you see that we have a circuit where we have some EMF with this E0 over here driving a voltage through A, S, and L, R, where L is the inductor, R is the resistor, and back again. You see we have a gap from B to A, so path B is not being considered. Now when the switch is flipped to B, we are bypassing the battery and we're just running whatever voltage we have, or EMF, through B, R, and L, and S. Alright, so with that, we could just, use a voltage loop real quick, nothing that we haven't seen before, or presumably haven't seen before. So what we can say is that for part A, the EMF in volts of this is equal to E equal negative L di dt. Again, that comes from the flux and Lenz's law and all that stuff. But we know that that's equal to IR, Ohm's law. So if we set this up and solve it for the current, what we see is that we actually have a homogeneous differential equation. Okay, di dt plus R over L, I equals 0. Okay, again, this is an ordinary differential equation, so we know pretty quickly what to do as far as finding a characteristic solution. We were told that we have initial condition at t equals 0, when the switch got flipped, that we had some current I0 from the battery, which was up E0 over R. But again, that's at t equals 0. And we know that these have a characteristic solution from the characteristic equations of A equal negative BT. Again, physically, we cannot have a positive in the exponential. That wouldn't make sense, seeing as how the current would drain out over time. So use your physical intuition. This is physics, by the way. So if we apply this initial condition and plugging it in for the differential equation, we can solve for the constants A and B. We've done this 1,000 times. It's just an initial value problem. The hard part is setting it up. So if we see that, then we have I at t equals 0. So we plug in 0 for t. We see that A equal negative B 0, and we know that e to the 0 goes to 1, thus implying that we have I0 equal A, and again we see that I0 was equal to epsilon, or not epsilon, E0, the EMF naught over R, so we have one constant done. Now if we plug in the form of this equation into the differential equation itself, we could solve for the other constant. So let's take the derivative of A e to the negative B t, and we see if we do this, we get A e to the negative bt times negative b, and that's also equal to negative R over L times I. So we'll also plug in A to the e to A times e to the negative bt for that I on the right hand side. We see that on both sides we have an A times e to the negative bt that cancel, and we have a negative sign that cancels. So even if we were to assume that this was a positive in the exponent, the negative from the differential equation would trump that and therefore put itself back into the exponent with the exponential, which would tell you again that it drains out over time. So everything physically would be consistent anyways. But anyways, this says that B is equal to R over L, and thus we can write I as a function of time as A times e to the negative bt is equal to E0 over R times the exponent with minus RL times t. Again, we've seen this negative exponent 1,000 times. But for B, the energy can be found from the power, since we know that power is the rate of work per time, and we know that work and energy are related. So we just take the integral with respect to time, and we see that W is equal to the integral of power dt, but we also know that power is I squared R, so we just substitute that in since we solved everything for the current. With that, we have work or energy as a function of an integral function for time. So our bounds on the integral go from 0 to infinity as time runs out, and we'll see that we get a characteristic damping or driving down of this. I don't even know if damping is accurate since we don't have R there, or something else there. But anyway, so if we keep chugging away at this and we plug in I squared, we get E squared, E naught squared over R squared, e to negative 2 RLT times R. So you see we get R's canceling. We can factor out the constants since this is an integral with respect to time. If you do a U sub, you get a factor of negative L over 2R out there. Pretty quick and easy, but the integral then is still evaluated from 0 to infinity. And we see that e to the negative infinity goes to 0, and e to the negative 0 is just e to the 0, which goes to negative 1, thanks to how we set up the bounds. And then you see we get a negative and a negative, which cancel, and we just do a bunch of hoopla magic here, just to set it up so that we can see a comparison pretty easy with part C. But all the forms in the box are correct. We just set it up to make it easy. With that being said, part C is asking the energy stored in the inductor. Well, we just know that that's W equal 1/2 Li squared. Again, this is at t equals 0, so we have W naught and I naught. And we saw that I naught was equal to E naught over R. And again, that's squared. So if we look and compare and contrast the above, we see that they're indeed the exact same thing as the power total energy delivered to the resistor. That's pretty darn cool.